So how many people are online? So this is a refresher course.
Yes.
Okay, good. Hello everyone. My name is Surhud, and I'm going to be talking about Introduction to Gravitational Lensing to you. So this set of lectures is devised between the two of us, myself and Anupreeta. And what we'll try to do is give a set of 3 lectures which will give you a background for what gravitational lensing is, how it can be useful, and whereon it is being used currently. So let's begin with this particular picture. So this is something that you may have actually seen or experienced by yourself. Have you ever gone to the house of mirrors like this? Right? So there are mirrors of different kinds of sizes and shapes, and the surfaces are bent in some weird ways. So if you look at that image, what do you think is causing? Like, what is the actual thing that is present which is leading to this kind of image configuration that you see? Are there 3 different is that woman that is standing there, is she really that tall? Or is she really this kind of having a big belly and so on? No, right? So when you look at things like this, you know that there is something funny which is going. Which means that, okay, there is one person who is standing in front, right? And then the light from that person, so the light which is reflected from that person, is going to that mirror surface, getting reflected from there, and then coming to you. Now something odd is going on at these mirror surfaces, and that's why you're seeing, first of all, 3 different images of the same object. Then you're seeing these different distortions that are happening, right? And if the speed of light was something that you could easily perceive, I mean, in day-to-day life, we don't perceive it that easily because light travels so fast. Then what would happen is, if that girl waved a hand, then one of these images would wave the hand at you first. Then the second one will do the same. And then the third one will. Right? This is because the time that it takes for light to go from when the person actually waved the hand to the mirror and then to come to you is slightly different because the path is not exactly the same. And so these slight differences in paths can also cause delays in how this image will start to change. Okay? So that is what we are going to do. So this is like mirror on the wall. You can see formation of multiple images. You can see magnifications and demagnifications happening at different places. And then the time of arrival between each of these different images is different. Right? So then these are some of the observable properties of these images that you can see. Okay? And so what we would like to know is, if you only observe these properties of these images, can you deduce something about the mirrors that are causing these distortions? Okay. And you can easily see that if you have a prior understanding of what this girl should look like, then you should be able to figure out, based on the images that you see, what these mirror surfaces look like. Okay. So something similar happens also in the real universe. And just like you are able to figure out these curvatures of these mirrors, you are able to figure out what is causing the curvature of space-time, what is there in between, which is causing these kind of different images. That is. And of course, it won't be images of a girl, it will be images of celestial objects. Okay? So in this particular picture here, for example, you see these big yellow blobs. These are galaxies in the foreground, so somewhere in between us. Then there are galaxies which are further away from us. So these blue blobs that you see here, these are images of galaxies which are very far away from us, much further than even those yellow galaxies. Okay, now what you see is that they are being distorted into these kind of weird shapes, and here as well, right? So there is a yellow blob here, and then a blue galaxy which is being distorted like this. So you could say that maybe this is a galaxy, but have you ever seen galaxies which look like this? No, galaxies don't look like this, right? So just like that girl that you saw in the mirror, these galaxies, these images of these galaxies have also been discovered. What is causing the distortion is the gravitational potential of it. Okay, so this fun bending of light that is happening, it can cause visually interesting phenomena. We can think about it as a Cheshire cat. You can see the uncanny similarity between them, right? And this one is another one where the snake is eating its own tail, right? So these kind of fun looking objects or mirages do happen in the sky. And they are not only fun, but they can be also very astrophysically useful. Okay? Because they really tell us something about what is going on, what is the mass of these objects that are there, how that mass is distributed, and so on and so forth. Okay? So the reason all of this happens is because light gets deflected when it passes near massive objects. So this is something that comes from the equivalence principle in general relativity. So you can imagine, for example, that there is a lift here, let's say this red lift, and if it goes at constant velocity, then at a certain point of time, delta t later, it will be here, so this blue one, and then delta t later, it will be at this green position, right? So let's suppose that there is a ray of light which started from here, and you are observing this ray of light. The light is traveling in straight lines, and so what will happen in the blue elevator at delta t time later, this light ray will reach here, and 2 delta t time later it will reach. Right? So if you are a person in the lift and you are trying to observe this light ray, what you will see is that it will go from here to here to here. So it still continues to travel in the straight line. So this is what happens if that lift is just moving up at a constant velocity. Now you can think what happens if instead the lift is an accelerating frame, right? Then what happens is initially you go in time delta t from here to here, but because it's accelerating, now this distance is larger, right? And so what you see is that light continues to travel in a straight line as observer who is sitting outside the lift will say, right? So it will be here, then here, and here. But someone who is inside the lift, that person will see that instead of a straight line, now this green point will be a little bit further down, right? And so you can see that if you are observing things in an accelerated frame, then you will start to see that there is this kind of a bending. Now, light is no longer traveling in a straight line. Okay? Now, whatever happens, this light deflection that we see in accelerated frames, that should also happen if you are having a frame which is sitting tight, but in a gravitational. That's what the principle states. And so gravity should be able to deflect light. Okay? This is something that Einstein said. Now, in order to get more quantitative estimates for what this deflection should look like, you have to start with the metric in the weak field. Well, suppose you have gone through GR, and so you should have seen this kind of a metric. So there's ds square, and then to the space component, I've added this 1 minus 2 phi s c square, and to the time component, there's this 1 plus 2 phi s c square. Phi is the Newtonian potential. Okay? And so if you look at this particular metric, you can ask, what is the trajectory that light will take? So light always travels with ds square equal to 0. And so you can put ds square equal to 0. Okay? And then try to figure out, just rearrange this, to figure out what will be the speed of light as measured by distance elements here and the time elements here. So you're thinking about light taking these different paths, and then ds square has to be 0 on those paths. And now you're trying to figure out what is the apparent speed of this. So if you do this ds square by dt square, rearrange this equation, it will look something like this. Right? So this 1 plus 2 phi by c square, and then 1 minus 2 phi by c square will go in the denominator. This c can come out. And so you see that the speed, the apparent speed that light takes, will develop this kind of a correction, right? As it goes close to massive objects. So this 1 plus 2 phi by c square, 1 minus 2 phi by c square, so you can again try to do Taylor expansions in order to figure out what this should look like. So this 1 minus 2 phi by c square can go up. And then you will have 1 plus 4 phi by c square raised to half, so that again goes to 1 plus 2 phi by c square. So you see that the speed of light now develops a correction. You will see that, well, if phi was positive, this will increase the speed of light, but these are gravitational potentials are negative, and so what you see is that the speed of light, the apparent speed of light, will decrease, even though it's traveling in vacuum, but it is traveling close to massive objects. Now, what happens when in any medium the speed of light decreases? So this is something that happens in, for example, your glasses, right? You do see that things start getting different, right? And so that's what is going to happen as well in terms of gravity. And in fact, Einstein was the first one to use these kind of equations to then figure out what these deflection angles should. There were actually attempts like this even before, but they did not have the theory. Once the theory of general relativity is put in there, then it is easy to derive some of these deflections. So in Einstein's original paper, the way he derived the deflections was according to this particular ray diagram. This is actually from Einstein's paper. So what you do is you take a wavefront, okay? And according to Huygens principle, each point of this wavefront you can propagate further, say delta t time later, and figure out, okay, where will be the, what will be the wavefront that will look like if it started from here, from here, from here, from here, and so on. And the envelope of these wavefronts, that is what will be the new wave, right? Now, if the speed of light was not varying at all, it was just c, then this will just remain parallel, right? So the light will continue to travel as it's in straight line, right? So these wavefronts will always be high. But instead, now if you have some massive object somewhere nearby, then what will happen is that at this location, the speed will be different compared to at this location, right? Depending upon how far that object is from this point or from this point. Right? So now what will happen is the speed is a little bit smaller, so it travels a smaller distance here compared to the point or the wavefront which starts from point P1. Right? So now you can see, if you now take the envelope, it will be something like this. So what has happened now is the wavefront which was like this, now it has become something like this. Right? So it's no longer parallel, which means that there is a deflection which has undergone. Right? So what is the difference in the speeds of light at this location compared to this location? You can just write it down as del c prime by del x times del x. Right? And so this del c prime, you can write it down in terms of the speed of light here. So you can see that there will be a derivative with respect to the potential which will enter. And so you see that there is a factor 2 phi by c del x times del x. Okay. So this is delta c prime. Okay? But what we want to know is the angle by which this deflection has happened. Okay? And so that angle will be this angle OP2 P1. And so if you want to calculate that particular angle, delta alpha, then this is related to the speed difference, delta c prime by delta x multiplied by delta k. Okay? Because it's the exact same time same, the only difference that you see is in this particular length. Okay? So this length divided by this distance P1, P2 is this small angle, alpha. So that's what we have used. So now you can substitute for del c prime by del x from here and put things in this equation. And you can see that you get minus 2 by c del phi by del x times delta t. Okay? And I multiply by c and I divide by c, so you get a c delta t c square. Right? This c delta t, I can call it as a path length by which the ray has propagated. So if you look at this, what it means is that you keep on accumulating small deflections along the path lengths that you travel, right? And these deflections are of the order of this gradient that you get for the potential with respect to x. Okay? So if you have 2 points P1 and P2, you can compute what is the gradient of the potential here, and then the light ray is traveling in this direction. So this gradient of the potential is in the perpendicular direction compared to the direction of motion of that light. Yes?
So why are we not taking the correction in time?
Correction in time?
Because even the time would slow down.
Right. So this particular metric that we have taken, it takes the time which is further away. Okay? And so it's the speed of light as measured from someone which is far away. That's the reason why. Otherwise, if you are there and then measuring time, these things also change. In fact, Einstein did not have this particular metric at that point of time. He did not have this term. And so what happened is he derived actually half of what the deflection should. Okay, so this total deflection angle is then the sum of these small deflections that you continue to accumulate as a function of your path that the light is traveling. And so then what you get is this alpha, when you integrate over delta alpha, you get this integral over the perpendicular gradient of the lensing potential, or of the gravitational potential, multiplied by this 2 by c square. You integrate over the unperturbed path of the light. Okay? So this is the equation that Einstein derived, except for this term too. Okay? So he did not have that term in the room. So then he was able to fix this particular equation before someone tried to confirm it observationally. Okay? And the person who confirmed this observationally was Eddington in a very famous experiment. So Arthur Eddington and his colleagues went to 2 different locations, one in Brazil, one in Principe, the island of Principe, and there they saw an eclipse. And during the eclipse, they tried to look at the positions of stars. Okay? So now what happens is, if the true position of star is here, the light coming from this star, it bends due to the gravitational potential of the sun, and then it reaches to you on the earth. From the earth, you think that every light always travels in straight lines, so because it comes like this here, you think that the actual position of the star is here, even though the real position is. Okay? So now what you can do is you can take some stars which are on this side, take some other stars which are on the other side. You know what their angle should have been if the sun was not in their path. Okay? But now because the sun is in their path, this angle will be different. So that's what they try to measure. Okay? So this deflection of light, as I said, is a consequence of the equivalence principle. For a point mass, you can actually carry out this particular integral, and you can show that this alpha is given by 4gm by c square divided by the impact parameter. Impact parameter is how far away the light travels away from this particular mass. Okay? Now, we can express it always in a vectorial form because this deflection is also a vector. And so that's why you see this psi divided by mod psi square. So if you just look at it in terms of a value, it will be just 1 over the impact parameter. But this allows you to write it down in a vectorial form. Okay, so let's see how this looks like. So this is, again, one of the original photographic plates. At that time, there were no CCDs, so they did not have CCDs to take camera, just like you have in the in iPhones or phones right now. So what they did is they had this sun, which was undergoing an eclipse, and then they imaged stars, okay, in the same field of view. Then what they did is 6 months later, once the sun was away from the field of these stars, they again took that image. Okay. Now these 2 images you can overlay on top of each other, and so what you are seeing is the overlay of that of those 2 images. So each star is now imaged in 2 different locations. One of them is the real position of the star, the other one is the apparent position after the deflection. Right? And so you can see that indeed the position of that star head. And if you go further and further away from the sun, you can see that the amount of deflection that you see, it is smaller and smaller and smaller. So this confirmed the prediction from general relativity of what exactly this difference should be, how it should scale as a function of distance away from the sun. So all these things were tested in that particular experiment, which was carried out by it. So this was pretty cool. The amount of deflection that you should see for some impact parameter which is close to the radius of the sun is about 1.75 arc seconds. If you try to do this calculation in Newtonian physics, so if you say that I have a massive object and I'm going to shoot some object which has a velocity v, and then because of the gravitational force of the sun, you will see that this object will also undergo a deflection. Right? And so if that object is not light, you can calculate what this deflection angle should be, and it turns out to be half of that value. So the fact that you see that it is indeed twice of that value was a great confirmation of general relativity, and this was one of the reasons why Einstein got really famous overnight. So Einstein, even though he was really brilliant, he actually missed out some of the things that you could use this particular deflection of light for. The kind of things that we use gravitational lensing for, a lot of these things were predicted by this particular person, Fritz Zwicky, in the 1930 in an article in the 1930s. So Einstein had published some of these calculations based on this suggestion made by R.W. Mendel, as you can see here, that a star can act as a gravitational lens. But Fritz Zwicky, he said that actually there are many more massive objects which can act as gravitational lenses. So Einstein thought that maybe you can see these deflections here just near the sun, but he never thought that this would be that useful. Okay? Because for distant stars, these deflections become smaller and smaller, and so he thought that this would not be that interesting in effect. But Fritz Zwicky, the pioneer as he was in fact the first person who also led to the discovery of dark matter. Maybe you have heard about this or you will hear about this. Okay? So he said that you can use this discovery of images of nebulae, which are being nebulae as at that time was another name for galaxies, because people were just trying to get warmed up to this idea that there could be these other galaxies which are lying on. And so he thought that these nebulae can act as gravitational lenses, so galaxies themselves can act as gravitational lenses, and you could do a number of these things with gravitational lenses. So he said it could furnish an additional test for general theory of relativity. He thought that these kind of gravitational lenses would enable us to see nebulae which are much further away. Okay, so just like you have telescopes, and with telescopes you can see things which are further away, you can use these gravitational lenses as cosmic telescopes to see things which are even further away, because it causes these objects to be magnified. Okay? So that's another thing that he said. Then the third thing that he said is that you can determine the masses of objects like galaxy clusters using this kind of. So Fritz Zwicky was really an oracle, because we are really doing all of these things now. They were not possible in the 1930s. Many of these things were not possible, but he did think about it, envision them, and then now it is being made into reality. So let's get to it. What is gravitational lensing? You should at least remember these things, even though you don't remember the equations. Bending of light due to the gravitational field of massive objects. And this bending can cause different phenomena. You can see multiple images of the same object. Okay? Those multiple images, if you see them, that is called something called strong gravitational lensing, where you are in such a field that you start to see all these distortions of galaxies, multiple images, strong arcs that I had shown you before. But then you can also be in something called a weak gravitational lensing regime, where you are so far away from the massive object which is causing the lensing that you don't form multiple images. Instead, the light bundles that are coming from you, they get distorted in a tiny lab. So that particular effect is called weak gravitational lensing. And the third effect we will learn about is called microlensing. So in microlensing, you can form multiple images, but these multiple images are not separated by a large distance on sky. So any given telescope, it has certain resolution, and so if the images are separated by something like micro arcseconds, it is very hard to resolve them. And so what instead you get are two images falling on top of each other. Okay? So now instead of getting light from just that single star, now you get two different images falling on top of each other, so the brightness of that star increases. So that thing is called microlens. So there are different forms of gravitational lensing, and you can use these different gravitational lensing forms in order to learn about the universe. So let's look at what are the things that you can do. It's kind of one tool to measure a lot of things. You can measure cosmological parameters of the universe. You can measure things like the initial mass function of stars, which means when stars form, if there is a certain amount of star formation that has happened, how do this star formation distributes in different masses? You can learn about that. You can understand the connection between galaxies and how galaxies form within their dark matter halos. You can search for extrasolar planets. Okay? You can do tests of general relativity. This is something that Sriki had talked about. You can learn about abundance of compact halo objects, things like primordial black holes, which are so small that their Schwarzschild radius is even smaller than the width of your head. Right? You can do this with lensing. You can understand the nature of dark matter. What is dark matter made up of? You can look at galaxies in the early universe, again, something that Fritz had told you. And then you can study black hole disks as well. Okay? So the accretion disks of black holes, what are their sizes? Many of these things can be done with gravitation. So let's try to learn about it and a little bit more of the mathematics behind. So as I said, there are three different things that we wanted to understand, right? Based on the images that I showed you in the beginning of the first slide, you want to know what are the locations at which you will form these different images. Okay? That's the first thing you want to know. You remember the picture of a girl, a single girl is the source, and then there are these three different images that you saw. So where exactly these images happen, that is the first thing that you would like. So how light gets deflected and how it relates to the formation of multiple images, that's the first thing. Second thing that we would like to understand is how do things get stretched. Okay? So how does magnification happen? This is the second part. And the third part we want to understand are the time delays between each of these. Okay? So these are the three things that we will try to derive in the lecture, in the rest of it. Okay? So let's look at a source which is somewhere here in the source plane. Okay? Then there is an arbitrary mass distribution here in something called a lens plane, and you as an observer are sitting here. What Einstein had derived previously was given a small mass m, point mass m, what is the deflection angle that you are expected to see? Okay, given the impact parameter, like where the light is coming from in an unperturbed manner, and then it gets perturbed. Right? So what that deflection angle is something that Einstein had calculated, and that number was 4 gm by c square divided by the impact parameter. Okay, so that was the deflection angle. Okay? And so, if you want to calculate if there is an arbitrary mass distribution here, and you want to calculate what is the deflection because of this arbitrary mass distribution, what you do is you divide this arbitrary mass distribution into smaller elements. Okay? And when you divide it into smaller elements, then you can say that, okay, there is a small mass dm here, and a small mass dm here, and a small mass dm here, and integrate. Now you can ask me, why have I considered only mass in this particular plane, and so on? The reason for this is virtually all astrophysically relevant cases that you see correspond to this kind of a configuration, where there is a source which is far away, then there is something which comes in between, okay, and then you are as an observer. So we can use something called a thin lens approximation because these distances are really far away, and the distance within which the mass of the lens is confined is typically very small. Most of the time, when light travels through the universe, it travels through voids, almost nothing. So it encounters almost. Once in a while, you will start to see these kind of configurations, and that's the reason why lensing happens. And so we'll consider this kind of a configuration. Okay. So now that there is a mass distribution here, if I wanted to know what is the small mass element here, dm, then you can write it down as a surface density times an area, right? So that surface density here is here, and times an area is here. So the area element, I have written it down as d2 psi prime. Is that clear? So now you get 4gm by c square, right? Or 4gdm by c square, and then 1 over the impact parameter. Now, because these deflection angles are vectors, every time the deflection by a point mass is done towards it or away from it, right? Because that's symmetry for it, right? The point mass is axially symmetric, and so the deflection that can happen, it will only be towards it or away from it. It cannot happen in some left or right direction. It will introduce handedness, right? And so that's why the direction is towards that length element, and so the deflection angle happens at this particular location psi is related to the difference between the location where the mass element is there and this psi. So psi minus psi prime tells you what this impact parameter is vectorially, right? And so that's the reason why you see this psi minus psi prime divided by modulus of psi minus psi prime. Okay. So is that clear? So we had two things. We wanted to check 4gm by c square divided by impact parameter. That is here, 4gm by c square divided by impact parameter. And the vectorial deflection that happens is towards the mass element. And the direction towards the mass element, if this is psi prime and this is psi, then it is psi minus psi prime. So we are trying to calculate what is the deflection angle at this location. Now this is due to a small mass element. If you want to calculate the total deflection angle, you have to do a vectorial summation, which means a vector integration in this case. And so you do an integration and get the total deflection. Okay. Is that clear? So simple mathematics, you started from the simple equation for the deflection for a point mass, and then now you're generalizing it to a mass distribution. Then, once you know, so that's the physics of it, right? So the physics tells you what the deflection angle should be. Now let's look at the geometry. So let's suppose that there is a lens here, Earth is here, source is here. So whatever diagram you saw previously, now I've just put it on a plane. Right? So there is light traveling from this source, it goes here, gets deflected by this angle alpha. We have calculated what this alpha is. What we want to do is to relate the position of the images that we will see with the true positions on star. Okay? So as an observer on Earth, if the lens was not here, light from the source would have traveled on this red line and you would have seen it. Right? So the angle with respect to the lens of the unperturbed ray is beta. Okay? So let's call that beta. Now because the light got deflected and came from like this to you here, you can extrapolate this ray. The image that you will see of that source will be somewhere. Right? And so the angle that the image makes with respect to the Earth lens direction, this is theta. So these are just names that I've given right now to figure out what the image positions will be. So the image position is theta, the true unperturbed position is beta. Now, the reason why this beta becomes theta is because of this deflection angle. So now what I can do is, I can define a new angle called this alpha. It's called the scale deflection angle. And notice that this scale deflection angle is related to alpha using these distances letters. So what are these distances? The first distance is between the earth and the deflector, that's why it's called dd. Okay. Then the distance between the lens and the source is called dds, so deflector and the source, so that's why dds. And the distance to the source from the earth to the source itself is ds. Right? So how are these two angles related? So if you take alpha, multiply by ds, then you get the distance, this particular distance. Okay? But this particular distance is also this alpha hat times dds. Okay? So now I have related this alpha, the scale deflection angle, with this alpha hat, which we had already calculated. Okay? So this is that equation. Alpha that you get here is dds divided by ds times alpha. It's simple geometry, nothing complicated. These distances, if you are not going to cosmological distances, these are just ordinary distances. But if you are looking at objects which are really, really far away, because you are converting angles to some physical distance here, these have to be angular diameter distances. This is something you should have studied in cosmology as well. These lectures will be. Is that right? You know about angular diameter distances or no? Yes, right? I mean, I see only you. Does everyone? It is covered, right? Okay. So these are angular diameters. Now what happens is these three angles are related in a very simple manner, right? Because beta plus this alpha scale deflection angle is equal to Q. And so you get this equation, beta is equal to theta minus alpha. Now notice I will try to make all these angles in bold. The reason for this is again the same, that all these deflections are vectorial deflections. And that's why these equation will be satisfied in a vectorial manner, not in just a beta is equal to theta minus alpha. You cannot just substitute. It's not a scalar equation, it's a vector equation. Okay? Is that clear? Okay. So to see how these are vectors, let me show you how this configuration looks in the plane of the sky. So I have shown you something which looks like this. So you are looking as if the Earth is here and the observer is here and so on and so forth. So instead of that, now I'm showing you what the locations of the lens and the source will look like on the plane of the sky. So let's suppose this is the lens, okay? And this is the original position of the source. Okay? So if the lens was not here, you would have observed the source there. Instead, what happens is the light from this object gets deflected due to the lens and the image forms at this location. Now the reason why this looks a little bit funny is because this lens I assumed to be having an arbitrary mass distribution. If it was axially symmetric, there is no reason why this image would lie to the right hand side. It would have either gone here or here. Right? But because my lens distribution is quite arbitrary, so this image can go to some other location. It does not have to lie on the lens source plane. But if the lens was axially symmetric, then it would lie on the lens source because of symmetry. There's no other way to go. Okay. So now it comes the vectorial form. So this beta is the vector joining the lens and the source. Okay. This was the angle between the the lens observer and the source, original source. So that's why it looks like an angle on the plane of the sky. Right? Similarly, the image that forms is this theta. So the deflection angle, the scale deflection angle is. So now you can see, you can look at it as a vectorial equation. So this beta vector is theta minus this alpha of theta. Okay?
You can just translate or could it be like some up and down and combination of that?
Yeah, exactly. So I mean, right now I've just shown it like this, but this could be here as well. Yeah, no problem. Yes, of course. Because I mean, there is no horizontal direction in space, right? Everything with respect to the lens center will be something which is like a circle, right? Or it depends upon the distribution itself. So this is, I mean, this horizontal thing has no. Is that clear? So this is a vectorial equation. Okay, so then we'll try to understand how to write this scale deflection angle. So we'll try to make some um, simple substitutions in order to recast that scale deflection angle in simple terms. So let's try to do that. So this alpha hat, you remember this equation that we had written down, 4g small dm by c square divided by the impact parameter. So this is simple. Now what I'm going to do is, instead of writing everything in terms of this physical distances in the length plane, I'm going to write it everything in terms of the angles in the plane of this. So if you want to convert a physical distance in the length plane into angles, you have to use again angular diameter distance to the deflector. Right? So dt times theta will be this psi prime. Right? So dt times theta prime will be psi prime, dt times theta will be psi. So this d2 psi prime, I can write it down as dd squares times d2 theta prime. Right? This is okay. This is just simple substitution. Similarly, this psi prime becomes dd times theta prime. Okay? This psi minus psi prime again becomes dd theta minus theta prime. This one will become dd square theta minus theta. So I've done nothing complicated here. And this equation was for the actual deflection angle. For the scale deflection angle, I have to put these two factors in front, dds by ds. So again, nothing complicated, just substitutions. And then what I can do is, again, I can rearrange. So what I can do is, I can take these things to the denominator here. I can gather all these dd squares and dd and whatnot, just cancel it out. And what you get is this particular expression, okay, for the scale deflection. So you get some 1 over pi, because I put a pi in here in the denominator. You get d2 theta prime, the sigma at dd theta prime divided by this quantity, theta minus theta prime divided by mod theta minus theta prime square. Again, simple arithmetic, nothing complicated. So what I can do is, you can look at this equation. This equation on the left hand side has no dimensions. This is an angle, right? Angle, deflection angle. So no dimensions here. This thing has no dimensions. This thing has no dimensions. So this also should be dimensionless. So you can see this is a surface density, which means this also needs to be a surface density. And so this surface density is something which is only made up of fundamental constants C and G, and then the distances, the geometry of the situation. Where is the source? Where is the lens? So this thing is called the critical surface density, and we'll see that it becomes important. So what I've done is, now I have recast this sigma divided by the critical surface density as a value called kappa, and just written it down. This should be kappa of theta prime. I'm sorry, I should not have this kind of a typo. And the critical surface density is defined in this particular line. So this tells you something about the efficiency of lensing. If your source is at an optimal location, then it makes lensing easier. Okay? Because your deflection angle can now really be large, even if your surface density of your mass is small. That's the reason why it's also called a lensing efficiency parameter. Okay. Okay, good. So what you got now is just a dimensionless equation. Everything is dimensionless in here. This is alpha, this is kappa, which is the surface density divided by the critical density, and all these other terms are dimensionless. So now if someone specifies a kappa for you, you should be able to figure out what the alpha is. Yes?
So how do we determine the
This distances, so if you know the cosmological parameters, and if you know the lens redshift and the source redshift, or the deflection redshift and the source redshift, then there is a formula which tells you how to go from cosmology and these redshifts to these distances. Maybe you have looked at these distances, so dd and ds you will know, but dds is complicated, right? So for dds, you have to take into account that the object that you observe is in the source plane itself. Okay? And so the physical distances are measured in the source plane. So you can always transform the moving distances into this particular distance. So this DDS for flat space, it turns out to be chi s minus chi d. So this is just the moving distance, the difference of the moving distances that I've taken. But then I have to account for a fact that there has to be another 1 plus z of the source just to go into the. So this is what it looks for flat universes. If you are not in flat universes, then this turns out to be like a f of k that you have. Okay. So now once you have that alpha and someone tells you a beta, so someone has given you an undeflected position. It should have been written somewhere. So if someone gives you this position beta, and I told you how to calculate alpha, now you can solve this equation to figure out what is theta. Now this is a nonlinear equation because alpha can have like 1 over theta square depending upon the distribution, mass distribution. And so because this is a nonlinear equation, you can have multiple solutions to this equation, which means a given source position, beta, can have multiple different theta values, okay, depending upon what this alpha is. So if I specify alpha, you can solve this equation to figure out what are the multiple positions. So we did our first job, just to get the positions of these different images that if someone has specified the lens potential. Okay, let's move further. Now, it turns out that rather than doing these complicated vectorial integrals, you can always simplify the problems in order to write in terms of something called a lensing potential. So let's look at how it works. So if you define a lensing potential like this, where psi is 1 over pi, and again the same kind of integral kappa theta prime d2 theta prime, but instead of theta minus theta prime divided by mod of theta minus theta prime square like this, instead of that you define something like a log or a natural log of this quantity. Okay? Now this is a scalar equation. Right? Because this is a scalar, you're doing all this integral, you get a scalar out of it. Now, it turns out that if you take this scalar and if you take a gradient of that potential with respect to this theta, then you can get back the equation for the scale deflection. So just like we have a potential in three-dimensional gravity, and if you want to compute a force, what you do is you take the gradient of the potential in order to get a force. So just like that, here we define a lensing potential, and the gradient of the lensing potential, this is in 2D gradient, it gives you the 2D deflection. So in gravitational physics, you have a 1 over r square, and that's why your potential goes as 1 over r. Here, you have a 1 over theta in the deflection angle, and so here you need a log of theta. Okay. So you can prove this, you can run through all the mathematics and show that if you take a gradient of this particular potential, you actually get back this equation. Okay. The next thing that you could do is this gradient of a potential will be a vector. Now you can take the divergence of this field so that you get a Laplacian. So you take this psi, you take a Laplacian of this psi, you can show that it will turn out to be 2 times this kappa. Okay. So just like in gravity, you have the Poisson equation. So you take the Laplacian of phi, the gravitational potential, it gives you the density. The same way, the Laplacian of this lensing potential, it is related to the lensing surface density or the surface density which is causing the lens. So this is similar to a Poisson equation, and in 2D now. So that's why it is useful to define things in terms of a lensing potential. And I will tell you why this becomes important as it will be soon. So now, yeah. No, yeah, here it should be. And then, this is because I'm taking the psi is at theta. So when I'm taking a Laplacian, you will get back at the same location theta. So what will happen is when you take the Laplacian, this will turn into a delta function. So 2 pi times a delta function. And so that then gives you this pi cancels out and you get a 2 times kappa of theta. Sorry about this embarrassing mistake. Should be theta. Okay, so now we are trying to figure out how the images get stretched. Okay, so when the images are getting stretched, what we are going to actually figure out is if there is a source position here and if there is a source position a little bit further out, how much do these deflection angles change? Or how much do the positions of the images that I see of these two objects which are close to each other, two sources which are close to each other, how much does that change? That's what we want to calculate. Okay? So this length equations relates the positions in the source plane to the positions in the image plane. It can be a one-to-many mapping, right? One source can be mapped into multiple different images, but at each image, it can get stretched in a different manner. So what we want to calculate is what is this stretching of each image. So this stretching of each image is related to the Jacobian of this transformation of going from the position in the source plane to the position in the image. Okay? What we want to know is how small differences in the source plane translate into differences in the image. So what you have to do is you have to take differentials like this, where you're trying to calculate how does theta, which is the image position, how does it change when you change the beta a little. And you want to calculate this magnification at the location of each image. So now notice that this particular thing, again, theta is a vector, beta is a vector. So how do you take this differentiation? So this means that there are 4 terms. So there is a theta x, theta y, beta x, beta y, or theta 1, theta 2, beta 1, beta 2. So now you get a matrix, which has 4 elements, del theta 1 by del beta 1, del theta 1 by del beta 2, del theta 2 by del beta 1, and then the last element, which is del theta 2 by del beta. So there are 4 different elements that are there. This thing is called a magnification matrix. So this is what we are going to derive. And this is where the potential becomes quite useful. Okay. So because these are vectors, it's easy to do in the component notation. Okay. So because we have a beta and a theta and both of them are vectors, I want is del beta I by del theta, where I and j can take the values 1 or 2. Right? So that I can work out all these components. Now remember, beta is equal to theta minus alpha of theta. So I will just write it on the board quickly. I will write it in the component form itself. So beta I is theta I minus alpha I. Right? So this is in the component form because actual vector form, I will just decompose it into the principal components, right, by defining certain axes. So now you take this equation in the vectorial form. What I want is del beta I by del theta j. So I have to take a partial differentiation with respect to theta j. Now what will happen? I will get a del theta I by del theta j, which is just delta ij. So if I want to do del theta 1 by del theta 2, it will be 0. Del theta 1 by del theta 1 is 1. So this becomes a chronicle delta. So that's what you see here, delta ij. And then this quantity, again, I have to differentiate with respect to a theta j. So that's what is shown. Del alpha I by del theta. Is that clear? Now alpha, as I said, was the gradient of the potential. And so alpha I, which is the ith component of this deflection angle, it should just be del psi by del theta. It's the gradient of the potential. And so I'm taking only the ith component of this gradient. And so alpha I is del psi by del theta I. I have to take another differentiation with respect to theta j. That's why you see this del 2 psi by del theta I del theta. Yeah? Yes, but it's easier to work out this and then we'll take the inverse. Okay? Indeed, thanks. That's important. So it is easier because the length equation is written as beta is theta minus alpha, and we can differentiate alpha with respect to theta, and so it is easier to do this rather than the alpha with respect to beta is complicated, right? And that's the reason why you write like this and then you take the inverse. So this magnification inverse matrix, that you can write it down now in this particular form. Okay? So how do we go from here to here? And what are the different components? So first of all, notice this is delta ij minus this del 2 psi by del theta I del theta j. Right? So now let's go back to the board and see if we can do some, again, mathematical jugglery. So this is, if you look at the equations, it will be 1 minus psi 1 1, 1 minus psi 2 2, right? And then this will be minus psi 1 2, minus psi 1, right? Now remember, the Laplacian of psi is 2 times kappa, which means this psi 1 1 plus psi 2 2 is equal to 2 times kappa. So what I can do is I can try to substitute this psi 1 1 psi 2 2 in terms of these kappas. Okay? So this kappa, as I said, so 2 times kappa is psi 1 1 plus psi 2 2. Right? And so I can use this kappa and then try to get rid of this psi 1 1 and psi 2. Once I do that, there will be another psi 2 2 which will enter in the first term. So what I can do is I can rewrite this whole matrix that I get in this particular form, where now I define gamma 1 as half of psi 1 1 minus psi 2. And this gamma 2 is just psi 1 2. So this is easy to understand, minus gamma 2 minus gamma 2. You can show that if you do 1 minus kappa minus gamma 1, where kappa is like this, gamma 1 is like this, you get 1 minus psi 1. Similarly, for this, again, substitute from here and here, you will get 1 minus psi 2. Okay? So your inverse magnification matrix, it looks something like this. Now I can just divide this particular term into two components. One is 1 minus kappa, 1 minus kappa, 0, 0. And then the other component looks like this. Remember, all these matrices, they are linear transformations which take things which are in the source plane to the image plane. How small differentials in the source plane, they transform into the image plane. That's what we are doing. So what this is saying, if let's suppose this was not present, then what you get is that there is a matrix here. If you apply a vector here, which is telling you some differentials in the source plane, how will they transform into image plane? So you can see this matrix looks like 1 minus kappa times an identity matrix. So any small differences in the source plane, they identically transform into the lens in the image plane as well. But they get this 1 minus kappa factor. So this 1 minus kappa just scales everything. Okay? So if there was a circle in the source plane, it will remain a circle if you just had only this one. It's just that the size of that circle will increase. So we'll see a magnification of that circle. What is this component? Now this is a little bit anisotropic. Okay? And so this causes shear. So a circle now no longer remains a circle, it transforms into an ellipse. Okay? If you have these things which are constant. So now given the potential, we can always calculate this because we have these relations. Right? Given a lensing potential, I can calculate psi 1 1, psi 2 2, define what is kappa, I can get the psi 1 2s, I can get the gamma 1 and gamma 2, I can put it in this equation, and I get the whole magnification. First we calculated where the image positions are. Now we are calculating how they will be magnified. So if your source is a circle like this, you apply this transformation, you go to the image plane. If you had only the first component, then this, if there are like small dots, on this particular source circle, then they will just go like this. They will remain a circle, but it will be magnified or demagnified. It could go in either. But because of the shear, now the circle doesn't remain a circle, but it becomes an ellipse. Now this ellipse has two things. One is the ellipticity of the ellipse, and the other is the direction. So you need two components to explain what is happening here. Right? And those two components are related to gamma 1. So the convergence, as it's called, this kappa, it magnifies uniformly, and the shear, which is this gamma 1, gamma 2, they distort things. They distort the shear. Okay? So is that clear now? So this is how you can derive what is the magnification of any of these images. So since it's almost time, what I'm going to do is I will stop here, and in the third lecture I will cover something related to time delays. So you can figure out what this time delays between each of these images are, and they are related to, as I said, the path differences that you get. So each image will travel through different paths, and so that relates to time delays, and so that's something that we will go through later in the third lecture. Okay. Good. So let's stop here, and I will take questions. I think we have time until 12:15, so I left 10 minutes for questions. If there are no questions, then we can go to the other part.
You calculate the lensing potential.
The lensing potential. Good. Yeah. So the lensing potential is this, right? So if someone has given me kappa, if someone tells me that your mass is distributed in the plane in this particular manner, then I can use this equation to compute the lensing potential. Right? So once the lensing potential is known, I can calculate the deflection angles. For a given source position, I can calculate the image positions also. In reality, what will happen is, you will never know the lensing potential, right? What you will have to do is you will have to see the images at different locations and say what is the lensing potential and the source position which will lead to these kind of things.
It always unique, like just one solution.
Right. So you need to check whether you get unique solutions or not. Of course, there are uncertainties in the measurements of the positions and so on and so forth. So that can lead to solutions which may be slightly different and still be consistent with the positions. That is, oftentimes you can say that okay, something. I mean, it depends upon how many constraints you get. So if you have just one position of the image, right? So let's suppose that that there is a source which only gets single image. Now you don't have enough constraints to figure out what is the source position plus what is the lensing potential. So of course you have multiple solutions. But once you have multiple images, then you will start to see that you have better and better constraints. So not everything you can invert, some of the things. And of course, if you use, again, magnifications of each of these images, then that also helps. Right? But that will come to later. Yes?
We use the linear magnification for
yes.
each of the objects. Is it like really possible? Because if we use for a linear magnification for one position and a linear magnification for another position, and for an object in between these two, can we just like superpose them, or we have to calculate?
No, you have to calculate. At every location, you have to calculate. You cannot superpose just in between something that is happening. So at every particular position, you have to calculate. The linearity is coming from the fact that I'm looking at only tiny differences in the beta values. Right? So let's consider there is a source, and the source has a certain size. Right? And so the difference in the beta value here and here and here and here is quite small. And that's the reason why we are taking a linear approach. As you get closer and closer to the lens, and if you are at a region where there is like high magnification, this linear approximation will break down. Then you have to deal with something called flexion and so on. So you can't just deal with shear in that case.
And I also
Yeah.
have another doubt. Like we take small dm masses of units and calculate the deflections, and then is it not that the gravitation causes the individual units and as on a whole consider using dr is totally different? You can't just superpose them.
No, so in this case, in the weak field limit, this superposition is not occurring. Yeah. So in the weak field limit, it can be done, this superposition, and that's the reason. Even the equation that we wrote down for the deflection only applies in the weak field limit, right? Otherwise, you can have all sorts of, like you have to do a full general relativistic calculation by taking into account the geodesics and where the paths of the light rays look, especially like near the positions of black holes, like you see the black hole shadows, the photon spheres, and so on. There you have to take into account the full theory of channel. Yeah. Any other questions?
That means in the strong field regime, we take into account the general relativistic mechanics type of.
Yeah, you have to consider the full metric, right? What I wrote down was the metric in the weak field, right? And from there we derive the deflection angles and so on. Once you have the full metric, you can always write down what the path of the light ray is. Yeah.
Like, can we like relate refractive index what we define over here?
Yeah.
It is dependent on gravitation.
Yes, indeed. So this C prime, for example, that we wrote, you can consider this C prime to be coming from like a refractive index of the medium. So vacuum develops a refractive index when you have a massive object here. Okay, any other questions? There are people online, so maybe I'll check if there are any questions from there. Where is this? Zoom. Oh, Zoom dropped out. What? Showing me as talking.
No, I think it's working fine, Surhud.
Working, right? Okay, good. Yeah. Oh, I can't see. Thank you. Otherwise, it would have been a nightmare.
Yeah.
So why can't I see? Maybe I need to exit that. So, are there any questions from the online audience? Please put them in chat or raise your hands.
None so far in the common chat.
Okay. Maybe I have 5 minutes. I can go through the last part then. Then I don't have to worry about trying to cover also the. Is that okay? Or no? Or are you tired? So there's a lot of mathematics, and I have put these slides on this tiny URL, etc. So you can always take a look. Okay? If you want to actually follow. And I have also my lecture notes which I have prepared for some IUCAA school that I had given. So most of this material is also available. So I can send those links to you. Okay, so 5 minutes. Okay, I promise I won't go over time now. So there is a source here again. This diagram you're used to, right? Now, what we are going to calculate is what is the difference in the path length if the light would have taken a direct path like this red line, compared to the path that it takes, the circuitous path. And so this extra path length, it will just be equal to AB plus BC, where what I've done is I've constructed like isosceles triangles. SCU is an isosceles triangle, and then OUA is another isosceles triangle. So because these are isosceles triangles, this path and this path is same. This path and this path is same. So the only extra path that is remaining is AB plus BC. Now this AB plus BC, I can write it down as B times BL, the length BL times this angle AUC. All these are very small angles. So I'm allowed to do all these kind of distance multiplied by angle, d times theta. So that's the extra path length. Right? Now, what is dl? dl is equal to dt, which is the distance between O and L, times this angle alpha. Okay, so it's actually, sorry, ub is what I'm talking about. And this distance ub, or I mean, these angles are quite close, and that's why it's alpha times dd. So that's what I will do. So alpha times dd times the angle AUC in radians. That's what we are doing. Now, what is this angle AUC? So the angle AUC is something that we want to work out. Now, this AUC plus AUO and CUS should be 180, right? Because this is a straight line. So all these three angles should add up to 180, right? So AUO, which is this angle, then CUS, which is this, and then AUC, they should add up to 180. Now, what is AUO? AUO is same as this angle because this is an isosceles triangle. So this plus this alpha angle should be 180 again. It's just a geometry, right? Angles sum up to 180. So when you do that, you can write down this particular angle in terms of the angle. So it turns out to be 90 minus AOU by 2. Similarly, here you can write the other angle CUS as 90 minus CSU by 2. Now you take this equation, there's 90 here, 90 here, 180 here, so you can all cancel it out and so on. And you can express this AUC in terms of AUU and CS. So you get AUU plus CSU by 2. Now what is AOU plus CSU by 2? What is this angle? So this just turns out to be alpha, and that is because, so this angle, right? This angle should be the same as the summation of this angle and this angle. So these are just like plain simple geometry things that you can use in order to write down what this extra path length is. So it looks like dd times alpha times this alpha by 2. And this alpha was the normal deflection angle, so you can write it down in terms of the scale deflection angle, which is this alpha. And so you have to add these distance factors, ds by ds. So now you can write down what the extra path length looks like. So it is half times alpha square times this distance factors. So again, all simple geometry, but you just have to go through one by one. And all these steps are written in the slides, so you can take a look again. If some of this seems confusing and I'm going too fast. So this alpha, I can write it down as theta minus beta the whole square. And you can see that this extra path length, I have now written it down in terms of the position of the image and the true position of the source. So this is the extra path. Now you can ask, why is light behaving like this, right? Light usually takes the shortest path. Instead of going from here to here, why is it going circuitously like this? So the answer lies in Farmer's principle. It is not the shortest path, but it's the shortest time. Okay? So now you can realize that if it was going to take this kind of path, then it would have to travel very slowly here, right? Because it's coming very close to the lens. So instead it decides that no, I should go a little bit farther away so that I can minimize my time to come towards. Okay? So this extra path that you're trying to see, what you can do is you can also work out, because of this extra path length, there is an extra time that is required. But then there is some time that you save because you have this gravitational time delay, which is affected. So what is this gravitational time? So this is related to the fact that rather than traveling straight, now you're traveling a little bit from a farther away. Right? So this dl by c prime is because the speed of light is changing, right? And let's work it out with respect to if the lens was not at all. Okay. So dl by c prime is the time taken to travel a small length element minus dl by c, which if the lens was not there, this is the time it would have taken. Right? Now, what you can write down is dl 1 over c prime minus 1 over c. You know how c prime is related to c, like this in the weak field limit. So you can work out what 1 over c prime minus 1 over c is. So in the and to leading order, this comes out to be 2 phi by c. So you take these equations. All these delays are happening at the location of the lens itself. So then there is a 1 plus zb which also comes about. Let's forget this 1 plus zb for the moment. But you get a dl 2 phi by c cube. Now remember that the deflection angles, they were gradient of the potential, gradient of the gravitational potential. And so what I'm going to do is I'm going to introduce this operator, which is a gradient inverse times the gradient. Okay. This allows me to take this gradient inside, so I get a gradient of 2 phi by c cube and integrated over all the length elements. That gradient is the small deflection that you get at each and every path length. Right? And so this gives you the total deflection angle when you integrate it. Okay? So you get a gradient inverse of the deflection angle. What is the gradient inverse of the deflection angle? So gradient of the lensing potential was the deflection angle. So gradient inverse of the deflection angle is just the lensing potential. So these gradients, you can convert them using distance factors into a gradient of theta and so on and so forth, so that you can write all of this down in terms of the lensing potential and some distances. So this extra time that you have to account for, that turns out to be related to the lensing potential that you have. So you have extra path length that you travel, and this extra time because you are going close to a massive object and traveling that particular or going through that particular range. So we have these two different time delays, and so now what we can do is to add these two different time delays up. You get half theta minus beta the whole square minus psi of theta. I have taken out some of the factors which are related to the dimensions out and defined this non-dimensional time delay, which is here. So this time delay surface, it tells you what is the time delay with respect to the unperturbed path. Okay? And if you take a gradient of this time delay surface, that is the Fermat principle, right? That you should come at the least amount of time. You have to modify that Fermat principle to say that it should not be the least amount of time, but it has to be one of these places where the gradient turns out to be. Now, if you take this equation, take a gradient, you get back the lens equation. So you can write all these things in terms of the time delay as well, and that light should have a stationary point, this time delay surface. So given a location beta, there are only certain positions which will be stationary for the time that it takes for that image to arrive to. And when you do that, you get back the lens equation, as you should. So we learned about how to get image positions, we learned about how to get magnifications, and we learned about this time. So these were the three things that we started with when we looked at the first slide, where I told you that page up. So these three things that were possible with this graph: the image positions, the magnifications, and the time delays. Those are your observables. You can use those observables to learn about the matter distribution. So what will happen tomorrow is you will learn about strong gravitational lensing when you have these multiple images, how you can use these multiple images to figure out what is the mass causing the deflection. So that's something that you will learn tomorrow. And then day after tomorrow, I will talk about weak gravitational lensing, where you don't see multiple images, but you just see these distortions. these distortions are also able to tell you something about the mass distribution. In fact, it turns out to be more useful because to form these multiple images, you have to be really aligned with the lens. And so these perfect alignments happen rarely. But weak deflections happen all the time. So you can make dark matter maps, you can study about how dark matter is distributed throughout the universe, learn about cosmological parameters and so on. So that is something that we'll take in the third lecture. Yes, I went overboard. Still, sorry. So maybe we can stop here and then you will see Anupreeta tomorrow and I will come back in the afternoon. You. Hey Prakash, there are no other questions, right, on the chat? Let's see.
No, sir.
Okay. So should I stop? What should I stop? Sharing?
Yeah, you can actually quit and
The recording as well, right?
maybe Santosh will take it. We can take it as.
Recording stopped.